Hello everyone and welcome to a new episode of All Things IDA. In today's episode I'm going to be reverse engineering a very simple malware. Now this malware will give us an opportunity to exercise a bunch of stuff we learned in previous videos. We're gonna let this malware unpack itself, we're gonna clean up the database and make sure the database is decompilable so we can understand what this malware does. Alright, let's get started. Alright, so let's disassemble this malware. So this malware is just 9.5 kilobytes. You can open it in IDA. And one important thing when we deal with malware in IDA, it is advisable that we select manual load. This will let us select which parts of the binary to be included. By default, for example, the header is not included. But when we select manual load, we will be able to bring in the resources, the PE header, and so on. We never know if a malware is going to be hiding code in the header, for example. So we want everything into the database. So make sure we select manual load, and then IDA will start asking us a bunch of questions. So which is the preferred loading image base? We're going to keep it at the default. And now it's asking us one by one. We want to load the text section. So here it automatically, I select don't show this message again, so it didn't ask me for data, iData and so on. It automatically brought them in. And then it asks me if I want to load the header. And here we have it. Now if I press Ctrl S, I have everything. And the header, I have resources and everything needed. Now since this is malicious, I'm gonna be using the Bochs debugger. So I'm gonna go to the debugger menu, select and Bochs. Now of course you have to make sure you have Bochs downloaded and installed on your machine, and you don't need anything more than that. So now I can, for example, put a breakpoint here, hit F9 and start debugging this malware. Before we do that, if I press Shift F3, there's only one function, and if I scroll here, there's a lot of data, just some data here, lots of data, some stuff here, undefined bytes, and so on. So this is clearly a packed program. Let's quickly take a look at the imports. Well, we have a bunch of imports, but I don't expect to find any cross-references. I don't even know if those imports are really what this malware is going to be using. But this is important to see the before state, and then once we clean it up, you see how different it will look like. Alright, let's run it. I hit F9 and the breakpoint hits. So here, for example, we have call door +5. This is going to call the next instruction. It's usually followed by a pop. So when we do the pop here, we should see EBX to contain the return address. So it should be 40100C. So here it's calling the next instruction, pop, and this is the next instruction here. Then they're XORing BX with BX, so to clear the lower 16 bits here. And this takes us to the image base. Here we are at the image base. Then, of course, now here we recognize this, the +3C ELFA new. You can press Shift F1, add, and import image.dos header. If we need to go into all those details, but I'm not gonna go into all those details. But here, ELFA new. Can press T, for example, and then to add to the image base ELFA new takes you to the anti-header. In the anti-header +14, so we can as well double click. For example, here you can see it's going to the size of optional headers, so it's skipping over all the header, leading eventually to the sections. But again, this is boring details. Let's just let it do its stuff. Let's keep on stepping. And so far nothing interesting. Push all. Okay, we have a call. Now I doubt that these are real functions, so I'm just gonna delete the function. Keep on tracing until I find something interesting and I will describe. So here set direction flag, load SD, STOSD. So, and then decrement EBX. EBX is 32. So this seems to be a transformation loop. We can see it. So load SD, it loads from ESI, and ESI has been modified already because after this. So here AX is, let's press 4 here by the way, shows them as words, and go to ESI. So they loaded this value here into EAX. They're gonna add to it some value, and they're gonna store it to EDI. EDI, they can also go to EDI. So they're gonna do it in place. So this is gonna be modified. Decrement and loop again. So we have to wait for this to finish. Now it's important to mention, to wait for this to finish, usually one would put a breakpoint and then let it run. But what if this decryption routine is gonna modify the code after here, so it will override your software breakpoint. So the best approach is to put a hardware on execute breakpoint. Like this, even if this code is gonna be modified, your breakpoint will still hit. Now, since I'm using Bochs, Bochs is a software emulator. It will never use the CC. It will internally wait until the instruction pointer reaches this point. So it is safe in Bochs to use a regular breakpoint. But otherwise, I would have to make sure it's a hardware breakpoint. But again, it won't make any difference under Bochs. Let it run, and you will notice that this instruction will change because this will decrypt it. So just F9, and here we have new code. So we can get rid of this, and we reveal more code, for example. Let's continue. Same story, set direction flag, XOR, loop. So again, another loop. Let's press F4. It has 23. Let's just wait for it here. Same story here. Let's press F4. Follow this one. Let's undefine all those because the code has been decrypting itself. So we have to redefine. Okay, it's coming here. Now I'm trying to take the fastest approach to finish the decryption routines. Okay, let's wait for some decryption loop. Okay, so here it's gonna go all the way up. There's no other way to exit, so we can safely wait for it here. And there's a nested loop, so this one as well, it's gonna loop again. We can wait for it here. And it finished the first one. Decrement ECX, so ECX is big, it's gonna repeat the whole thing all over again. So as well, I can safely wait for it here. And same story, this could be changing, so make sure you put the right breakpoint. I'm gonna hit F4 to run to cursor up to this point here. And I'm assuming this will change as well. So F4. Okay, new code has been uncovered. Let's just undefine and make code again. Keep tracing. XOR. Another XOR here as well. So ECX as well is a big number, so let's wait for it here. EDX as well. Okay, so it's gonna keep doing that loop multiple times, so let's wait for it here. Alright, now we have better code. Let's make undefined, make code, and look here, we have a string, light compressor. Great. Okay, it seems we did a bunch of the initial decompression. And now I feel we're dealing with something else, and we see now what we're dealing with. Alright, let's see now what happens. So function call, push A. Alright, look at this pattern here. Push large f as 0, move ESP this here, these two instructions, install a new structured exception handler. Now in Win32 targets, IDA has the SEH list built in, so I can open that window and we can see after we executed those two instructions here, these led to installing a new exception handler. And here we have the top level exception handler, which is the Bochs operating system, but the newly installed exception handler is this one here. So we can double click, and if you want we can put a breakpoint here, wait for that breakpoint to trigger. Alright, here we have a call up to here, and here they do look like a string. Now we don't want to guess, I can right click and synchronize with EIP. So here at the call, after the call directly, we have a string user32. So we can press U and then A. This is not really a function. I'm going to delete the function. And this is not a function. So calling past the string is like pushing to the offset of the string. So this is a common technique as well in assembly code to push the offset of a string, and we can directly inline the string within the text section. So that's what they did here. So by simply calling past that string, the stack will point to the return address, which is the address after the call. So they pushed to this one. So the address of user32 string has been already pushed. Now we have pushed some number, and as well look at this here. As well we have another string. So here this is the call, and here this is the string here that's undefined, and make here. Alright, let's just fix it real quick here. So register class here and here. Alright, so let's see what is this call doing. Alright, going here as well, let's just select and undefined, make sure we have clean stuff, follow it, let's make clean code. Alright, so let's continue, and here they're accessing the PEB and then going over the LDR module and so on. So this is something I covered here, shellcode API resolution, exploring PEB, LDR data and so on. So what they're doing is apparently they want to resolve APIs by accessing the export table directly from the loaded modules. So let's wait for it here, continue tracing. Gonna enable basic block boundaries just for clarity. And here let's see what is being pushed here. So apparently it already went through the bunch of modules, and here I recognize this is directly accessing the export directory and so on. And from the looks of it, they are not really scanning all the modules loaded, they're looking for the kernel 32. And they're starting to load the exported symbols. And then they get the first exported symbol in kernel 32. They're gonna then get the next one, next one, next one. Let's open the code stack window. This was pushed. This is like a hash with C. Then it entered this function, and that's where we are right now. So this value here that was pushed, this is the hash, and this here is the name of the export, and there will be so many exports in kernel 32. So if you go here to kernel 32, it's gonna be hashing every single function, and then after it hashes it, it wants to compare with the past hash. If it matches, this is resolving an API by hash. If I follow this function, decompile it real quick, it does look like it's doing some hashing. Now we don't care about the implementation. I'm gonna call it hash string. It takes a string and some value. Let's first prototype this. It returns an unsigned int for the hash. It's a const character pointer, let's say str. I don't know if that argument is a pointer or not. I'm just gonna make it an integer and assume we're passing 0 all the time. So it's gonna hash the first API acquired lock, and it is not what the user passed. So it's gonna again load the next name from the export address table, and this is the next name, which is here as well. It's the same name. It's gonna keep on hashing those until it finds the match. And so there is a way for us. Well, first of all, this algorithm doesn't necessarily have to be in any common database. It could be a custom hashing algorithm. So how can we figure out the hashes of all those? Well, the good thing is we can leverage Appcall. So if I have a way to enumerate all those programmatically, which I have, then I can use Appcall to hash every single string. And like this, I can build a table. So I'm going to show you how we can do that. So the first thing is I want a list of all the names in kernel 32. Now, as I said, if you're going to do this by hand, it's here. We can go to the modules window. We have kernel 32, for example, and we have the names. I can right click copy all, maybe, and clean them up, for example. Or I can use the debug names APIs. So we have in the name.hpp, we have function called getDebugNames. It returns a vector of EAs, addresses, and names, which is here, which is the address of it and the name. So we can use getDebugNames if we give it a range. So the range we want to give is the boundaries of kernel 32. So like this, we can get the debug names within the boundaries of that module. And so this is the code here. So I made a function called getModuleDebugNames. Give it a module name. And the first thing I do is go over the modules and make sure I find the module by name. M is going to be a module info object, so it will give me name, size, base, and so on. So if I find it, then great. Then what I do, I get the name. It's going to be full pass. So for example, C, Windows, and kernel 32, for example. .dll. I get the name without the, so here I try to get the kernel 32 dot, because IDA internally will take the base name, add underscore, and then that will be the full debug name. So what I do is simply get the full pass, get the base name, get rid of the extension, and then based on the len of the name without the extension, anything after is the API name. This is a generic technique that works under any debugger anyway, so it's any file format. But otherwise, I could have parsed the PE file using some libraries like PE file and then enumerate the exports. But here I'm doing this dance here just to get the base name and skip the dot so I can get past the underscore. And then I get the debug names for the module base, module name plus size. And I build the dictionary and return it. And now I have all the names. Then I call using Appcall the hash string method. So here let's just do one example by hand. For example, get package ID and say id.api.appcall.hash string. So in order to be able to do that, as I said, we have to have the proper prototype. So we have the function name hash string and it has a prototype. So now we can call it like that, and here we have, this is the hash. So if I call this in a loop, I should be able to retrieve all of them. So if we run this script, I should be able to have a table. Now, if I want, I can emit this in the form of a header file. So for example, let's try to do that. Let's say enum API hashes, and let's here print the end, and here let's do like that, print. All right, so here is we're gonna the key here is we don't need the key, which is the EA. We're gonna just take the name, so we're gonna call it, for example, k32 underscore. We're gonna take the V, which is the name, equals the hash. That should be good enough. For example, and like that. Let's try and let's run it. So just activate the script. Now it's gonna take a while because it's calling in the context of the malware inside the Bochs emulation environment. It's leveraging the hashing function as a black box function. So if that hashing function was complicated and you don't want to lift it, you don't have to. So here we have here, let's make this C++. Here k32, this looks good to me. And I can, for example, bring this here, copy it, and go to the Shift F1 window, insert here, paste this one, and we have created it. Now if I go back to the stack window and press M, I have the API hash here, load library, for example. And since here, this function, we're gonna see that this is the function we're in. It's just simply looking by hash. So let's wait for it to find it. It's gonna find it, and here it found it, and it's gonna return the value load library, and it's gonna call it. So here is setting up the stack and jumps to load library. It's gonna call it, it's gonna enter the Bochs emulator, it's gonna load library, and it loaded user 32 because this is what was pushed. So this one we can call API by hash. That's the function. And then here as well, they're calling past another string, and they're pushing the handle return. So they load library user 32, they push user 32, and they're gonna call something else. They're gonna call get proc address. So get proc address takes a module handle and the procedure to resolve. So they wanna resolve register class A. So they're gonna call get proc address to return the value of this API. And here we have register class A. And now they're gonna call it. So they're gonna call register class A with a null pointer. And that will cause a crash. And this is a way to detect, for example, emulators. If this malware is being run in some antivirus sandbox or emulator, and the emulator doesn't know how to properly emulate the side effects of calling such an API with null, then it will halt and it won't continue. But so it's expecting an exception, and usually this should be an access violation, not null pointer access. And that's why as well we have seen it add an exception handler earlier. So it's gonna be here. So this is a way to detect weak emulators. So now it's gonna call register class. Register class should raise an exception. Now luckily in a Bochs emulator, we don't know how to handle this. It's not even handled in Bochs. We can see here it's an undefined API code. It doesn't have any custom code. So this will not cause an exception. But luckily, the halt instruction is gonna trigger the exception and it's gonna achieve the same side effect. Now, if this malware writer didn't put a halt, maybe put an infinite loop, for example, just keeps on looping, then we couldn't continue with Bochs easily. But we are lucky in this case because of the halt, which will also give us an exception. Now, the malware writer could also maybe check the exception code to see if it's access violation versus privilege instruction, for example. So calling here register class with null pointer, we're not going to do anything, nothing happened. But the halt, we have a privilege instruction, which if I continue stepping, I'm gonna change the exception here and say suspend to the pass, don't suspend, pass to the application and resume. It should eventually come to the exception handler here. So it came here, we have here an exception handler. Now, I know in the exception handler, we're gonna be dealing with the context. So we're gonna import the context type. And here, this is the context. So here, and we can now follow what they put into EIP. Just double click. And we can follow it. This is the resume point. That's where the exception handler, once it returns, the exception handler changed the EIP. And it would return to this point here. So I'm gonna simply wait for it here. And we can see we are still in the same function. So that function is a standalone function that does nothing except try to detect the emulator. So let's just let it run. Okay, now it's gonna pop back the installed exception handler. So here we should see that exception handler here, it should disappear. And here we don't have exception handler anymore. And alright, so this one here, I would say here detect AV emulators, for example. And let's follow this function as well. Let's see here. Alright, as well here we have the same pattern. They're gonna install another exception handler, and in a bit here we'll see it's the exception handler here. So this is another exception handler. Let's press T. Okay, so this is gonna resume to the EIP plus 2. And let's also show the opcodes. Let's just show 4 opcodes. And they're using the int3 followed by an op. So int3 as well will trigger an exception. So if I step over here, yes, single step. And here we have the breakpoint exception. We're gonna change the exception here. I say also pass to the application. Now, this is good whenever we pass to the application, especially if the application doesn't want to be debugged. This is a common trick. So we just, when IDA prompts us, we simply change the definition, pass to the application, log the exception, and okay, and yes, pass to the application. Now this should take us to the exception handler. Here now it's in the Bochs operating system. Let's just run to go directly to the exception handler. So gonna increment twice, so we can also press enter here, follow it. We can see. So the exception happened here. It incremented the IP by 2. So we're gonna be returning after those 2 instructions here. Now, what's the point of this? So they're gonna do this, then they're gonna read the timestamp here counter, and then they're gonna call again and they're gonna read rdtsc, and they're gonna store the value of the tsc. And this is a timing check. So if we have a heavy debugger or an emulator, the timing might vary between the trip to go to the kernel and dispatch the exception and so on. So this is a timing check that can detect certain emulators. So they're gonna do this in a loop 4 times, build a measurement table for how fast it took to dispatch that interrupt, and then they're gonna do some computation and compare against a threshold. If they're not happy with the measurement and the speed, they're gonna halt. Otherwise, they're gonna return normally. So I'm gonna press F9. Let's remove the breakpoint from the exception handler. And we did pass the checks. So this function had no effect on the Bochs emulator. We were not detected. Let's continue. As well here, what they're doing is they're trying to scan for the image base. So we can see here they're going one page after the other. So let's see where AX is here. They're almost there. So no, here they're gonna get it here. So it's gonna end it. This is the image base. This is the MZ header. Okay, they want the image base for some reason. Again, I'm not going into all the details. Alright, this is definitely something related to virtual unlock or protect or whatever. Let's press M. You can know it's virtual unlock. So here they are allocating some memory. We can also press M here for the protection, allocating execute read write, and with the size, the ECX, and so on. And then this is important. So here what they're doing apparently is they're relocating themselves to the newly allocated memory. Probably the packer was already in the same location as the original code, but since now the unpacking is happening, they want to move out of the way to restore back the original code on top of where the packer exists. So it's also a good technique. So for example, we can have here some classical packers, the way they do it. For example, they take .text and they pack it, and let's say .data, they also pack it, but then they have here the unpacker code, and they don't have to do the relocation. So the unpacker code is in its own section. It unpacks in place, for example. But here in Lighty's case, it seems that the I don't know where is the .text originally, but the unpacker is apparently as well here on top of the text. So now it's gonna dynamically allocate memory, move its code to the dynamic memory, put the unpacker here so that it can restore the packed code. So it needs to move itself. And so here now, if we see the source, so let's go to ESI. It's gonna move itself from the Lighty compressor string. It's gonna move 14B5 into the newly allocated memory, into here. So you see after the repeat move SP, you can follow it here. It relocated itself, so it copied most of the things. Now, if you had software breakpoints, the debugger will not keep track, so this copy will copy the software breakpoints as well. And then the copied code is not authentic because it has been patched with the software breakpoint. So as well, you have to be aware of such a scenario. In our case, we do have breakpoints, but Bochs breakpoints don't show. Now it's gonna jump to somewhere inside that packer, we are in a debug segment, so that means the allocated memory, and it's doing some stuff. Again, I'm gonna scan quickly, um, not necessarily wait on all the details. Just let's finish. Let's let this one exit. Okay, let's see this one, pressing M. This is global unlock. This is the same function that was called API by hash, but since it has been relocated, of course it doesn't have the same name. The original address had that name, but this is the same function. So they did global unlock here as well. It's not important. Virtual protect. Here, okay, this is the ELFA new and so on. Let's see what they're moving. Okay, so they did unpack the full headers. They're gonna move it. So here we can see the actual original header. They're gonna move it to on top of the existing header. So this is the header, but this was the packer's header. Now they're gonna restore the unpacked programs as header. Is it only the headers they're restoring? Yeah, here. So basically they're restoring less than a page, just like one kilobyte. All right, and let's see as well what they are moving here. Okay, let's see where. All right, they're moving to the first section some stuff. It's okay. And yeah, here I can recognize this size here. This size is image section header. So image section header size. So now they're moving the original sections. So putting the sections. So here is the size of image section header. So okay, let's go to the next section and let's restore it. So here, if you see, this is here, and they're gonna restore to here somewhere. So they're rebuilding the PE file. It's not important. Global free, they're gonna call global free. Let's rename this as it is. So now they finish with some of the dynamic allocated memory. Let's see what they're doing here. Get module. I feel now they're gonna start doing the API resolution. So here's again, see if the DLL is loaded or loaded already. If not, they're gonna load it, and they're gonna start doing API resolution. So here we can see this should be get proc address indeed. So they're restoring the imports, and this is one of the imports, shell 32. This is the functions they want to restore, shell notify icon. And they're gonna store it here into the original import address table. So here, for example, so here at EDI, let's mark this as IAT, and we'll assume that here there will be a bunch of resolved APIs. So let this store, and let's go to EDI -4, press Ctrl O, and this is the first resolved API. And we can wait for it to finish. I recognize this constant as well. This is the size of image import descriptor. So this is really the classical workflow of an unpacker, where it will first decrypt the code, maybe apply the relocations, and then do the import resolution, and finally jump to the original entry point. So here they're resolving one import descriptor after the other. Okay, let's just wait for it to finish. Okay, there's no more import descriptor name, so this is the end of the API resolution here. Let's wait for it. Okay, it finished resolving everything. If I go back to IAT and just press Ctrl O, for example, you can see. And now the order could be different. So it's not like gonna be, could be resolving them out of order, but from here, let's undefine all of those. This is no longer the malware's start. Let's undefine and press Ctrl O, undefine. This used to be an entry point, but they overrode it. Okay, this is a resolved API. And these are all the pointers. So let's just try to guess how big it is. So yeah, we can wait all the way until here. Let's make Ctrl O here. Yeah, this one. Okay. So it looks like all the imports are from here to here. So edit, let's make a, let's call it idata2, for example. And we're gonna make an array as big as this whole thing. So I'm gonna select this and make an array to create everything as an offset. Now I have everything as an offset. And they're not an, okay, let's break the array. We don't need the array. They're individual pointers. Now we need to rename the pointers. So I'm gonna also select the range and Alt F9, insert. I'm gonna go to IDA and apply the rename import IDC script from IDA IDC. Double click. What did this do is simply rename the pointers accordingly. Now for making it look even nice, I will press Alt S to edit the segment and give it the extern class. I'm gonna uncheck debugger segment, make it loader segment, and now I have something looking like a natural iData segment. So now we have recovered the iData. Let's continue. Just trying to see if there's anything relevant here. Let's see this one here. Global unlock again. Okay, let's wait for it here and here. This is looping here. Maybe here. This looks more reasonable that it's finishing up. So I'm gonna put a breakpoint here. Let the loader does whatever it wants to do. Let it finish. And I'm hoping by this point it will transition from the debug segment to the original entry point. So let's see. I'm gonna hit F9. Okay. And step. And here we are back into the text. And this time it seems we have something much more readable, I would say, with string references and some API calls and so on. I'm gonna mark this location for now, call it EOP, and I'm gonna make sure I take snapshots. So I'm gonna debugger here and take snapshots. So I'm gonna capture the state of the Unpacked program. Here we have captured it. Now if I stop debugging, you should have that state captured and persistent in its unpacked form. Now let me stop debugging and try to clean up this binary. Okay, so if I go now to the OEP, indeed I have the OEP and it looks nice. I have some text here. I have a bunch of strings here. I don't like them to be in .text. So I'm gonna take all those strings here and put them, also we don't have to do that step, but I would like to edit segment create and put them in .data. Just create a new segment called .data. Alright, now I have a data segment. I have the header I don't need anymore. I'll delete the segment. Edit, segment, delete. iData, let's call it just iData instead of iData2, but this is the actual iData. We can see cross-references from the code. So I have the iData, I have the data here with the strings, and I have the text. And look here as well in the legend. We'll see if we can clean things more. Okay, so we can jump here, for example. All right. Now here it feels to me all those. Okay, we have a table here. It's used. Okay. All right. Here this table is gonna be used, and here I don't know if this is gonna be useful anymore. So I don't even see cross references to those. We can delete those, or we can keep them up to us. Let's see here, cross reference. Let's just keep it, it's fine. As for this iData, this definitely is not useful anymore, so I'm gonna segment delete it. And this data here as well, this is the compressor's code. We no longer need it, so I'm gonna delete it. This iData here, this is what the original segment was called. It doesn't seem useful, and the resource, we loaded it optimistically, we didn't need it. We can delete this segment. And this iData also can delete it. Okay, so now we have an actual iData, we have the dot data, we have the text, we have something that has no functions. It's okay, we can create a function here. And we have some data elements here. And okay, let's just get rid of this. I don't want this. Edit, segment, create. So to delete these, I'm gonna just make a segment and delete it. So I'm just gonna call it temp, for example, and I get rid of it, and now it looks much better. Now I'm gonna right click and reanalyze. It finished, and now the original entry point is no longer valid. This was the packer's entry point. So if I go to EOP, this is the actual entry point. So I can call it start, for example. And if I want it to be available here, I can just simply use add entry. So the API.add entry, and we will see add entry will let us add it. So here all we need to do is give it the position. So ordinal, I'm gonna say add entry, let's say 1, EA is here, name is start, okay, let's say original entry point, and make code, it's already code, okay, and we added the entry. So now if I press Ctrl E, this is the actual EOP. Okay, now if I hit tab, I should be able to see a nice decompilation. Now we can start analyzing the program. So for example here, we have some function here, open key requery. So I can call this, for example, requery. Just quick naming. I'm not gonna go into details. Here, for example, let's call this. Here is a create process. Show window. It's gonna be one of the. I'm gonna press M. One of the SW. Show window, I think show window normal. Here the flags, we'll have to go to the startup flags and import the flags. This one is gonna be the size of the startup info, and here I'm assuming is gonna be something like memset, for example. Yeah, clear memory. So here is the buffer. Let's say it's a character pointer. This is the size. Let's call this clear buff, for example. and just create a process. Let's call this create proc, and here send message wm close destroy, and we can just keep on systematically annotating all the functions. If we go to the entry point, let's just quickly take a look at this one. So here, let's call this set val. Well, apparently they're trying to disable most antivirus software. So they're gonna disable a bunch of antiviruses and firewalls and so on. We're gonna enumerate key, what's the sub key that was passed, browser helper, and so on. Enumerate and delete, etc. Set val, create thread. Before we create the thread here, get system directory. Okay, so it's gonna get the system directory. Then they're gonna go over an array of locations where they will retrieve the payload. So they have a bunch of payloads here, not payloads but sources. In case one of the sites go down, they have another source. So they have a bunch of alternatives, and if it fails, it will go over until it succeeds. It will download the file into win any VSTR. So it's gonna attempt to download the second file and to the system. Let's call this download payload, and then sleep 1000. Create thread. Let's see the thread procedure. Let's see. Load icon. This is a bit of social engineering. Apparently they're gonna do this icon here. It will show up at the tray and it will lie to you, just try to scare you. And this thread procedure here, window procedure, so they have a window as well. So what's this message you see? WM. I don't know if this is one of those messages. Could be a custom message. This the, I think is HWND wparam. Let's try to find the prototype for the default window procedure. So handle message wparam. I forgot the message. Okay, and so on. So here this is for the destroy. WND proc. This is creating a window as well. I can notify and so on. But with this level of documentation, I mean, there is nothing really that is obscure anymore. We can just simply take our time and reverse the remainder of this malware and document it fully. Alright, so that's it for today. What we covered is how to analyze malware using the Bochs debugger. We covered a bunch of anti-debugging tricks, anti-emulation tricks, discussed the structured exception handler, how to use the debugger correctly when it comes to self-modifying code and software breakpoints, and to prefer hardware breakpoints in certain scenarios. We also covered how to reconstruct the binary after it gets unpacked by creating the independent iData segments, cleaning up other segments we don't need, and adding a new entry. And then we decompile the code in a shallow manner just to describe the gist of this malware. Thank you, and I'll see you next time.